ask me the question. Okay, so let's start. IV regression model is one of the very helpful topics that we study in econometrics in general. So instrumental regression model is one of the very important models that is used in order to overcome any problem related to internally invalid model. And when I say a model that is internally invalid, I mean the model that might have some problems coming from omitted variables or wrong functional form, simultaneous causality, or any other misspecification errors. So the instrumental regression model is used to deal with these types of econometric issues. So the main outline of today's lecture is as follows. I'm going to start by giving you an introduction, or I'm just going to remind you about the OLS assumption. What was the OLS assumption? And now we're violating it, and we're using the instrumental variable regression to deal with this violation. We're going to talk about something very important, which is the conditions for a valid instrumental variable, IV instrumental variable. Okay, and the word valid is very important. Okay, so we're going to have a specific definition of what do you mean by valid. And then the next point is I'm going to give you two examples. One example is related to the textbook that you have. So I'm going to just go over one of the examples that you already have on your textbook, and another example that is very helpful. And then I'm going to have a representation of the IV model with just two axes. Okay, just a simple model with just two axes. And we're going to talk about a terminology called identification. Okay, and what do we mean by identification? We're going to talk about how to estimate the IV regression model. Okay, and I'm not sure whether we will have time to go up to this point, but I'm just going to write it. So we're going to talk about the general form of the IV model, or the IV regression model. Okay, because here I started with just a simple one that just had two axes, but in general, we have to expand this one to go all the way up to xk and possibly other values. Okay, so to start here, I just want to remind you of what the OLS assumes, right? The OLS has a certain assumption, and the assumption is, so the OLS assumes that the correlation between, you know this already, right? The regressives and the error term is zero. In other words, you can write it this way, or expectation between xi and the error term, or you can write it ei. Well, I'm going to write it ui because this is what I always write for you. Ui is equal to 0. So this is the big assumption, more or less. There is no connection between the error term and the x. So it's like this. If I do have any covariance between xi and ui, which is equal to any covariance in terms of expectations, from writing it in expectations operator, then it's going to be like this, minus expectation of x, expectation of u. And now, because I already know that this part is assumed to be zero, okay, we know already that the OLS assumes that the mean expectation of UI, which is the mean of the error term, has a center, like the mean is equal to zero, right? Or the error term distribution has a center, is centered on the zero. In other words, it's written like this. The error term is assumed to be distributed as a normal distribution with the center mean zero, variance one. So it is centered on the zero, okay? So this is actually the expectation of UI. The expectation of UI or the center or the mean. If this is assumed to be zero, then this whole part is gone, right? Zero times the expectation of xi is just equal to zero. So I would be actually left with expectation of xi ui, right? Which is again assumed to be zero. And that's why we got this kind of a shortcut. So the shortcut is coming from this fact. The covariance is divided into two components, expectation xi ui minus expectation of x times expectation of ui. And given that the expectation of ui is zero, then I have the second part is gone, and I'm left with the expectation of xi ui. So this is our big assumption. Like actually our first topic was based on this assumption. And if I do have this assumption, this is a guarantee, like we are guaranteeing that we are going to have consistent estimators, right? So if I do have this assumption satisfied, that there is no connection between xi and ui, then I'm gonna have consistent estimators. So just to remind you, if I have like a model like this, the assumption is about these two. Connection between these two is zero, no connection, right? And if I do have any connection between these two, then I'm gonna have inconsistent estimators. So if this connection again is zero, which is again, this is what the OLS assumes. If this happens, then consistent beta 0 and beta 1, and these are estimated, consistent estimators, okay? However, in our topic number 2, we discussed the violation of OLS assumptions, right? We said, I cannot always have a connection 0. Xi might be correlated with factors that are left from this regression or excluded from this regression, and we call them other factors, right? So might be the case that other factors, or you can call it, or you can actually add to the other factors anything that is random component, right? If you're talking about, I'm sorry for my spelling. So if you're talking about the demand and the price and that's it, of course the error term has other random components. Let's say what's going on now in the world, right, with the virus. This is a random component. No one was expecting this, but still, if this is the price, the prices are affected by known factors, right, and unknown random components. So in real life, I would say like in reality, we have most of the OLS, this nice word of assumptions, most of the OLS assumptions are violated. And this is what we had in topic 2. So when these are violated, whether because of I forgot certain variables, or I omitted certain variables, right? I had a mistake in some of the functional form of the model, right? I have some errors in variables, whether I made a mistake or I had wrong approximation. What else? Simultaneous causality. Causality, right? It's not all of these possibilities would make my model internally invalid, right? My model would be internally invalid. And then any of these problems would create a link between xi and the error term. So if the model is internally invalid, so I would have something like xi, ui will never be unequal to 0. It will have some number. Okay, so the covariance between xi and ui will not be equal to 0. It will be certain number. Okay, so what is the consequence of that? The parameters beta 0, beta 1, beta k will be inconsistent, right? So these parameters will not be consistent. What do you mean by consistency? Again, I keep saying consistency every time. So as the sample size increases, my estimator, let me call it J, supposed to converge to the true beta J, right? With a very high degree of probability. This is what we call consistency. It's like biasedness, right? My estimator is unbiased, but with the biasness assumption or unbiasedness assumption, we don't assume what happens to the sample size. So consistency is similar to the unbiased assumption, which means that the expectation of beta J is equal to the true beta J. So this is what we call that my estimate is unbiased. But when I talk about consistency, I attach to the definition the sample, what happens to the sample size. So as the sample size increases, if I have inconsistent estimators, then I'm not going to be able to reach this consistency assumption, or the beta hat J will not approach to beta J with high degree of probability. Okay, so if I have this problem, right? If I have the problem of the connection between xi and ui that is not equal to 0. This is a problem, right? We call x here is endogenous. So if x is connected with the error term, then it's a problem, and we call it endogenous. So x is endogenous, or we call it endogeneity problem, right? So the endogeneity problem is the connection between x and the error term coming from any of the problems that, you know, simultaneous causality, wrong functional form, omitting an important variable, and so on. So we have to think about ways to deal with this. To overcome this problem, endogeneity problem, the solution is use IV regression model. What is the IV regression model? So the IV regression model is used in order to overcome the endogeneity problem. So what do we mean by IV? So let's again look at our model. Here's our problem, this connection, right? So I want to break this connection. I want to try to think about a variable that I can use instead of xi and is able to solve the problems that I have with xi. So let's, for example, assume that I have a variable, let's call it z. So I need a variable z that is a good representative of x. So we have like this z has a good connection with x, it has a good correlation with x, it's a good representative of x. Okay, so I need a variable called z. And at the meantime, I need this z to be not connected with the error term. So it solves the problem of indigeneity. I needed to solve this problem. So we come to the two conditions for a valid instrumental variable, or here I call it z. Okay, just a name. So what are these two conditions? I need this zi to satisfy two important conditions. Number one, it has to be correlated with xi. Or in other words, you can think of it as it has to well represent xi. Or you can say I need the correlation between zi and xi to be not equal to 0. I need this correlation to be equal to something. Okay? I really don't care whether this correlation is positive or negative, but I need some number, right? So if I have certain number or certain correlation, then I need to, I can use this z as a good representative of x. And as you might expect, I'm just talking about correlation. But for our course, we'll not just use correlation, we will have to use a formal test. But I'm just giving you like the broad idea or the general idea about the conditions. This condition is called instrument relevance. Okay, so I need to satisfy the first condition, which is called instrument relevance. I also need to, number two, it has so it has to be not correlated, as you might expect, with UI. In other words, I need the correlation between zi and the error term to definitely be equal to 0. And this condition, we call it instrument exogenite. Okay, so I need two important conditions. I need instrument relevance, instrument exogeneity, and if I have this one and this one, I call it a valid IV. So we can write it here that a valid IV has to be relevant IV plus exogenous IV. And I'm saying plus because it cannot be or, it has to be and, okay? So you keep looking for a variable that you can use in order to overcome the endogeneity problem that is experienced with having X. So I'm looking for a variable Z that is relevant, connected with X, exogenous, not connected with the editor. So Let me give you an example. And this example from your textbook, it will make the idea easy to understand. So in the IV chapter, I think it's page 515, I guess, but you can always check. So the example, I want to find, or I'm estimating a model which is score, the final exam score, as a function with a certain intercept, plus how it is affected by the lectures that you miss, or we're gonna call it skip, okay? Plus editor. So this is final exam score. And this is lectures missed, okay? Now, I'm sure that when I'm looking at this model, skipped and the error term, they might be connected. Because if I think about this error term has factors like the student motivation, the student ability, you have family income, and of course, just keep going. You have so many factors that we can add here, right? All these are considered omitted variables. Now, the problem is, if I think about this model, there must be some connection between skipping class and the factors included here, right? So when I think about it, the correlation between skip and the error term, I'm sure that it's not equal to 0. It's equal to something. So this means there is violation of OLS assumption. And this means that beta 0 and or beta naught and beta 1 would be inconsistent. Okay, so I'm sure that skip can be correlated with the person's motivation. If I'm very motivated, I will not skip classes. If I have high ability, it's usually connected with not skipping classes, right? Family income, I'm not sure, but we can test it, right? Whether if your family income is connected with skipping classes, or students coming from rich families, they don't skip classes, or is it the opposite? I'm not 100% sure about this, but what I'm sure about is motivation and ability have a strong connection with not skipping classes. Now, if I have a violation and these are inconsistent, then I need to do something. Look for an IV estimator. And I should actually be more specific. Look for a valid, right? Because the validity is a very important word. A valid IV estimator, or an IV instrumental variable. It's not an estimator. Instrumental variable, okay? And we call it whatever, Z or anything. Now, we need to keep thinking, like IV regression models is one of these topics that it's not easy to estimate because it requires a lot of thinking about, okay, now I need a variable that is connected with skipped, has a good correlation with skipped, and at the same time is not correlated with other factors affecting the final exam score, you know, and you have to have it as and not or. So one of the IV for skip is distance, okay? So and this is what you have it in your example. So I need an IV for skip. This is what you need to look for. So the condition for this IV is number 1, I need this IV correlated with skip. Okay, so this is my first condition, which we call it relevance. In other words, I need the correlation between this IV, if I don't know what is the name of this IV yet, and skip to be not equal to 0. And then you can keep thinking about this. One of the instruments is distance to campus, and this is what you have in your textbook. And the idea is the longer the distance, right, or the higher the distance, you expect more skipping classes, right? More skip. So there is a positive. I really don't care whether it's a positive or negative relationship, but I care about that it makes sense that we expect some correlation. Okay? So here we expect that when you live far away from campus, you would probably miss more classes, holding constant your motivation, your ability, and other factors. Okay? So this is the first thing. So you actually can write it this way, that the correlation between distance and skip is not equal to 0. Okay, so this is the first one, which is about relevance.
Ask a question about this then?
Yeah, sure.
So for example, on like, I know we don't have any more assignments, but like we have a quiz. Would you be, if we did this in Stata, would you be giving us other variables that we could check to see,
yeah.
or would we have to make one?
No. I would never leave you make one. In my dissertation, my PhD dissertation, I spent 6 months to find an instrument. So I will not, I will not let you do that. I would definitely give you the set of possible instruments, and you would have to check it, right? And so far we haven't done any tests yet. We're just saying correlation, and as you know, we always do like a formal test. So after maybe next week, end of next week, you will learn what are the formal tests to be done, but definitely I would give you all the instruments you need.
All right, thank you.
Sure. All right, and next thing is, I need also, which is our second condition, I need an IV that is not directly related to other factors affecting score. Okay? When I say other factors affecting score, in your mind, understand I mean UI, because UI represents the other factors. Okay, so so you want something like this. I want the correlation between this IV and error term to be equal to 0. Okay? This is one of the very hard assumptions to satisfy. Like maybe number one, which is relevance assumption, is relatively easy to find variables that are correlated with your regressors, but it's really very, very hard to find a variable that is totally disconnected or the connection is insignificant with other factors affecting your dependent variables. So when I said I spent 6 months to find my instrument, I spent most of the time just on number 2, which is the exogenity assumption. So when you try to think about the distance, right? So apply this to our example, the correlation between distance to campus and UI. Is it really equal to 0? So when I think about what are the possible variables to be here, I have here, for example, as I said, ability, motivation, age, so many other things. But one of the things that can make this connection not equal to 0 is family income. If you think about family income, and family income, it is the case that if family income is high, you will, or when the family income is high, or families, or rich families in general, they put their kids indoor, right? So the higher the family income, the smaller is the distance to campus. Okay? Why? Because usually the case, rich family is most likely, right, put kids in dorms. So whether this is actually equal to zero, we need to check that. But we have like this is as a potential instrument that we need still to go into formal test and check. But we hope that the connection could be, for example, like a correlation of whatever negative 1.2, for example, but whether this is statistically significant or not. So we will need to check that. So this is an example, okay, where IV is used and where distance is used as the instrument, and this is called the exogeneity assumption. Okay. Another example that I like, which is so the other example, which is you have this cigarettes sold, cigarettes sold, or the sales of cigarettes, and is equal to beta naught plus beta 1 price plus error term. Okay, and suppose that you're collecting this for I equal 1 to n, and suppose you're doing it over the US states, for example, 50 states, for example, and then now I'm sure that, so this is the sales, and this is the price. Definitely the price is connected with other factors included here. Any factor that you can think of, right? Price, you will find some connection with price. So price here definitely is an endogenous factor and has some connection with the other term. So I need to correct for that. So you need to find an instrument. One of the instruments that is used for the example of the cigarette sold is the state sales tax. And this is used as an instrumental variable. And the assumption is we are 100% sure that there is a correlation between the price and the sales tax. Okay? And this correlation is definitely equal to something. And we're not 100% sure about the second one, but we need to test it. So the second one is about the correlation between the error term and sales tax. And we need it to be equal to zero. If you have like some justification or reasons to believe that the sales tax is not correlated with other factors affecting the sales of cigarettes, then you can use it. So you start with having something that makes sense, and then you go ahead and perform formal tests. Okay, so this is based on the idea that if you don't have any reason to expect.
Can I ask another question?
Yeah.
Is there no order for correlation tests or testing? Like
No.
putting sales tax, then price, or price and sales tax?
No, just
Okay.
notation. So here what I'm writing inside the bracket is just a notation. And if you start with sales tax first and the error term or the price and sales tax, doesn't matter.
Thank you.
Mm-hmm. I just wrote sales tax in the second one because I just want to make it easy to read.
Hi, Professor. I have another question.
Yes, honey.
I just want to know that in our model, we can't find all the variables. So is that a common thing that we will need an instrument variable to represent some variables?
Can you ask me the question again? I can't understand you.
I mean, in our model, we can't find all the variables.
In the error model, you're saying?
I mean, there will always be omitted variables in our model, right?
Oh, yes. Mm-hmm.
So does that mean that we always need an instrument variables?
So there is some stage that you need to pass. You need to have something called the base model, right? What is the base model? You have all the variables that are having the major impact on Y, and you're supposed to be leaving out in the error term the things that have minor effects, okay? So there might be some connection between the error term and some of the included variables still. You need to test whether this connection is important, or you can just get like, don't think about it, right? What I have in the examples here is just a model that definitely is incomplete, right?
Okay.
Definitely is incomplete. If I'm doing this as a project, I would tell you where are other variables, right? Where are the other variables affecting the cigarettes sold? You need to put here at least 5 to 6 variables. And then if you still have a problem of indigeneity, if you have created your main model and you still think that you have indigeneity and you test for it and you find there is indigeneity, then you can use IV regression.
Okay.
It's very common actually to use IV regression because most of the model, as you said, even if you include like the base model, you still have some indigeneity that is coming from one of the, of the things that I mentioned at the beginning, right? So when I mentioned for you the omitted variable, wrong functional form, errors in variables, simultaneous causality, you have something, right? You always have a certain problem. So it's very common to use it. But the number one thing that you need to do first is to pass the stage of getting your complete model. You're done with getting your complete model, you still have an issue, then just go ahead and use IV regression model.
So I want to know that if the R square or adjusted R square is very high, does that mean that there is smaller probability for you to have a omitted variable problem? So you
if you have a high R square, the R square is all about the explanation of the model. It will not tell you anything about indigeneity.
Okay.
Right? It's all about how it is computed, right? It's computed as ESS over TSS. This is all what the R square is going to tell you. Even the adjusted, it's the same equation, but adjusted for degrees of freedom. So it will not tell you anything about indigeneity issue. The indigeneity issue can be checked by the correlation between X and the error term. This is the only way that you can say something about indigeneity issue. And so far, what we have covered in today's lecture, we don't have the tools yet. We haven't covered the tools yet to check this indigeneity, right? I'm just telling you that, okay, we have indigeneity because it makes sense that I have indigeneity. Okay, let's overcome it. Let's deal with it. Let's find an IV for it. But by the end of next week, you should be able to perform the test and do the formal test to overcome it.
Okay, thank you.
Any other
questions? Can I ask one more question?
Yeah.
So let's say you do the test and it turns out that the correlation between the error and sales tax isn't equal to 0. How would you find, like, if you don't find a variable that you can sub into the model that is a valid IV, can you just not do the test? Or what if none exists?
You mean a variable does not exist?
Like either that a variable doesn't exist or you don't have one.
Yeah, then you won't be able to use the IV, right? You have to spend time to think about what would be the possible variable that I can get that satisfies these two conditions at the same time. So as I said, this one is easy to satisfy, but our problem is with this one, right? So when, as you said, what if I did this correlation and it's not equal to 0, then you cannot use it. Just go back and look for another instrument. So you keep going and checking. And when I said I spent 6 months, this is actually not bad because you cannot find, sometimes you cannot really find an instrument that works for your model. Okay, so that's why it is actually one of the disadvantages of using this method, because sometimes it's very hard to find an instrumental variable that can satisfy the two conditions. So that can be called a valid, I mean.
All right, thank you.
Sure. Okay, so all right, so we have covered 2 examples. Let's go ahead and talk about the model that has 2 x's. So suppose that, and I want to talk here about the idea of identification. So suppose that I have this model yi is equal to, and then I have x1i plus alpha 2 x2i plus ui. Now we are expanding the model. We don't just have one x that is problematic. I actually have two x's that are problematic, because now suppose that, or assume that x1 and x2 are endogenous. Now we know what is the meaning of endogenous. Endogenous, that the correlation between this and this is not equal to 0. The correlation between this and this is not equal to 0. It's equal to something. Okay, so if this is the case, then alpha hat 1 and alpha hat 1 and alpha hat 2, they will be inconsistent, right? So we are just repeating what I said before, inconsistent. So what we need to do is we have to use IV estimators, okay? So for each x, you need at least one. So for each x, yeah, you need at least one. So there must be at least one instrument. So I want you to think that I have x1, x2. I need for this one, I need z1 for this one, and I need z2 for this one. And it would be actually better if I have more z's, right? So I have 3 z's, 3 instruments to represent 2 x's. So the connection or the number of endogenous variables versus the number of IVs is called identification. So suppose that we're going to talk about this in terms of, or the number of x's is counted in terms of k, as we usually do. And suppose that the z's are counted in m, okay? So I have here, in this case, I have k equal to m equal 3, okay? So the relationship between the number of instruments versus the number of endogenous variables, or the number of problematic variables, we call x1 and x2 problematic variables because they are connected with x, would give us different terminologies. So the first one is if k, or if m, let me say, if m is greater than k, so this one we say the coefficients. So these coefficients are said to be over-identified. Over-identified, this is an important word. So actually this is the best case scenario. I do have the number of instruments exceeding the number of endogenous variables. So this is actually good because I have more information, right? And I'm assuming that these are valid, these are exogenous. So I'm using these that are good representative of X, and they are also endogenous. So it's actually the best case. Suppose that I have, this case, if M is less than K, this is what we call coefficients are said to be under identified. And this is actually the worst case because you have less instruments than the number of problematic variables. And actually, you will not be able to estimate your model in this case, right? So you have to choose either this one or get it exactly. So this one, the coefficients are set to be exactly identified. Okay, so this is just a notation. So when I give you a certain number of instruments, you compare it with the number of endogenous variables. And this is the best case when I have more instruments than my problematic variables. So I have more correction to my model than my problematic variables, or at least I'm getting this one. So this is your best preference, the second best, and this is actually, don't go with this one. We don't use under-identified coefficients. Makes it like problematic to estimate. So I want to understand that like this one, the under-identification creates a problem. Basically, you don't have enough IV to represent the endogenous axis. Okay? If I have extra instruments, which is the over-identified case, or equal instruments, which is the exactly identified case, this does not create any problem in the estimation of the IV regression model. Okay, so you can either go with the
question.
Yeah.
Did you just say that it is better to have the over identified version, or then so that's like the best one, and then exactly identified, and then we don't prefer the under identified?
Yes.
Okay.
Yes. Yes. Okay, because actually with the under identification, you will not be able to estimate the model. You have like less instruments to be used to correct for your problem. Okay, so you will not be able to use it in order to estimate. So we're just making sure that we're avoiding this situation or this case. Okay. Right, let's move to the next, which is how to estimate. So the IV regression model. So how can we estimate? I'm assuming that we have passed the first stage of finding a valid instrument. So you're now done with this. So you got your valid Z that is relevant and exogenous. So you're done with this part. And what I mentioned to you is just using correlations, but next week, I'm going to show you a test to make sure that your instruments are relevant. We're not just going to depend on a correlation. The correlation is just for, as a starting point, you can say, but you have actually to perform a formal test. So we're going to do this formal test next week. We're going to do a formal test here, but today I'm just going to talk about the estimation, assuming that I passed this stage of getting the valid instrument and use it in my estimation. So the method used is called the two-stage least squares. This is a very famous, the TSLS. And as the name suggests, it actually goes into two stages. So stage one, what do we do in stage one? So it actually takes this, you can think of stage one as a filter, okay? So you want to take your X and filter it into two components. A component that is problematic, correlated with the error term, and a part that is non-problematic, non-correlated with the error term. So you want to filter your X, you want to filter your endogenous variables. So we call, what we do in stage one is basically you decompose, or stage one decomposes X into two components. Okay, so what do you do by the first component? And the first component is, we call it problematic component, what is correlated with the editor, and the other which is good. So it's problem-free component. Okay, so this is in your mind. Remember, this one is correlated with UI, uncorrelated with UI. So you kind of need to divide it into two parts. I'm going to be using the ZI, your instrument, in order to extract the good part of X. So how you can do that? So suppose that I'm just assuming that my instrument is called ZI. So we're going to extract the good part of X by doing this estimation, which we call the first stage. So you regress Xi on the instrument, and of course there is an other term that's called Vi, okay? And when you look at this regression, which we call the first stage regression, you're regressing your X over Z. And I'm assuming that this C is already valid, endogenous, so I'm kind of sure about the significance of this one, statistically significant impact on X. And it's not, and it's exogenous, so it's not correlated with the error term of the original regression. So you can think of it, I don't know why my X is so big, so I'm just making this here. So this part is, you can call it the good part of X, okay? So you can call it the part of X predicted by Z or by the IV, okay? And if by the IV, and if the IV is good, then this is actually, or this part is correlated with the error term, right? Why? Since, and this is in your mind, since ZI is uncorrelated with UR, or the other term, okay? So I'm getting the part, this part is the good part, because this one will be telling you what's the value of X at 0, Z, what's the slope between Z and X. So this whole part is the part predicted by Z. It's the part that is non-problematic, or the good part of X, because it's exogenous, coming from Z, and Z is actually exogenous. This is the part which we call problematic part, okay? Or the part of X not, this is very important, explained. So this part is not explained by the IV or ZI. So if it is not explained by ZI, then this is the part that is still endogenous, right? So I filtered X into a part that is exogenous and a part that is still endogenous. So you can actually think about it like this. So the good part is, this whole part is exogenous X. This part is endogenous X. And of course, you want to maximize this as much as possible, minimize this as much as possible. And you can do that by choosing a good Z. So I can have like multiple Z's and I'm trying them. And actually I would be choosing the one that maximize, like the one that has the highest explanation or highest R square of the regression, right? Because this means that Z would be explaining the variability of X, and assuming that that Z is already exogenous, so I can maximize the exogenous part of X. Okay, so what we do here is just, you're going to be doing like just the regular OLS estimation, the one that you know, you just regress X, Z, and that's it, right? And this is just assuming I have a very simple model where just I have one X, and next week I'm going to show you an expanded version. What if I have multiple X's, multiple Z's, and how can I deal with it? So next, what is the second stage? The second stage, or stage 2, so In stage 2, you're going to be using your output that you got from stage 1. In stage 1, I filtered out X into the good part, the bad part. Now I'm going to be using the good part. I will forget about the bad part of X. So what you're going to do here is you're going to use the non-problematic part of X, which is equal, like remember, this part is equal. No. So this part is equal, which is alpha hat 0 plus alpha hat 1 C. So this is the part that you want to use, okay? And you're going to use it in the regression, okay? So now you can call this one as X hat I. And now you use this one in the main regression model. So my main regression model was like this. And if you remember, like this is like yi is equal to beta 0 plus beta 1 xi plus ui. And I had this connection between these two. So we found a z for this one. Now I'm going to, this is my main regression, okay? Now I'm going to be replacing the x with xi hat. So we're going to be regressing beta 0 plus beta 1 xi hat, okay, plus ui. So what you did is you have replaced the original x with the good part of x after you have filtered out the x, right? So you have filtered out the x into good part and a bad part. You have taken the good part and you have inserted it into your main regression model. So instead of regressing this one, this is going to be your main model, okay? And the output that you get, so whatever you're going to get here, let's say, let me call the coefficients different names so that you are not confused between the main model and the modified model, let's call it. So let me call this one as lambda 0 plus lambda 1. So this is the modified version of your main model. Okay? And of course, you shouldn't expect to get the same intercept. You shouldn't expect to get the same slope because the x has changed. Of course, they're going to be very close as long as the z is a good representative of x. So the coefficients that you get from here, this one, delta node, we call it TSLS and TSLS. So the intercept and the delta 1, these are going to be consistent estimators. And these are the two-stage least-squared coefficients, okay? And as I said, like this IV estimator is not only a proxy for the endogenous variable, but it's also used as a tool to remove the random component of this endogenous variable. So it acts as not only as a proxy, like not only as a representative, which is the relevance test. Representative is reflected by the relevance test, but it's also used to remove the problematic random components in the endogenous variable. Any questions? So these are the estimated ones, and these are supposed to be now consistent. The ones that we were supposed to get from our main model, which are here, beta hat node and beta hat 1, were inconsistent estimators because x and u were connected. Okay. Now we are assuming that these two are not connected because xi is the good part, is the exogenous part that is not connected with the error curve. Any question? Okay, so let's keep going. I actually have the time to show you the general form. So let me show you the general forms. They have 6 minutes, so which is good. So let's see the general form of the IV regression model. So I'm saying general form because whatever I have showed you before is just like simple, right? I just have one X and I'm getting one Z for it, and that's it. But in real life, in real models, in your project, for example, you can have multiple X's, or you have already multiple X's. Some of them might be problematic, some of them might not be problematic. Some need their replacement by looking for an IV, some others might not need a replacement. You can use them as they are. So in general, our general form would be like this. Yi is equal to beta naught plus beta 1 x1 I plus beta k x k I plus. So suppose that, let's keep the x's as being our endogenous problematic variables. Okay. I might have other variables that are not problematic, they are actually exogenous, or actually they are random. Okay, they are not connected with anything, they just happen. So let's call them as another name. So let's extend the model by saying, okay, this is k plus 1, and I can have a variable named w1i plus beta k plus r w r I, and suppose that the w's are good variables. Okay, so these are actually by nature they are exogenous, so they are not problematic. So I really don't care about it in creating any problem for me. Okay, so these are actually exogenous, and of course the I goes from 1 to n. Okay, so these endogenous variables are my problem now. I need to deal with these endogenous variables by looking for instruments. And if I have here k equal to the number of endogenous variables, right, which are the number of x's, then I need to have z that is at least, okay, so the number of z's that we use here n, so the number of z's they need to be at least equal to the k, or preferably over identified. So I prefer actually this one, right? But this is my highest preference, to have a model that is over identified. Okay, if you can't, then you go with the exactly identified. Okay, so let's say we have n equal k. So let's take the worst case. It's not the worst, the second best case, and how the first stage looks like. Okay, so we need to find, okay, maybe you can think about this for next week. I want you to write down stage 1, how the stage 1 would look like, how stage 2 would look like. And you can actually use, what is it? You can use whatever we have covered about stages. Okay, here. Okay, so you can use the stage 1 and stage 2. Okay, here's stage 1. Okay, here's stage 1. Okay. So you can use whatever we have done here and think about how you can expand this equation if I have more than one x and more than one z. Okay, so as a hint, you will not only have one equation. So if I have k x's, then I'm going to repeat this one for x1, for x2, for xk. Okay, and if I'm trying, like, my main objective from stage number 1 is to extract the exogenous part of x, then I have to be including anything that is exogenous in my model. So these are exogenous. So I can use them in the first stage to extract any exogenous variability in X. So next week we're gonna start from this slide. So we're gonna be talking about stage 1 and stage 2, but you can always think about it, try to think about it, and how can you expand the model with multiple X's and multiple Z's and multiple exogenous variables. All right. Okay, so I'm going to stop here, and I'll see you on Tuesday of next week. And have a great weekend.
Thank you.
Thank you.
Thank you.
Thank you.